So, good evening, everyone. It seems that I'm with a tough audience tonight. So, I'm going to start with an anecdote, and I take this proudly because past few years I have been hanging around with data scientists. And when you go to these, get-togethers with data scientists, do you know what the first question for a data scientist is to another one? So, how is your doctorate going? Are you already a doctor? And, I'm hanging in there and, staring at my toes saying that, don't mind me, I'm just a security guy. I'm doing an unlawful data science here, so please go easy on me, sir. There is a history and story to this. This originates actually around 2018, 19. This research that I have been doing, it has been standing time, I hope. And does anyone know, about a security conference called CCC, Chaos Communications Conference, in Germany, between Christmas and New Year, every year for 40 years? Okay, please check out. Really fun place to be. I have been there for years, and that's where all of this began. Because I was listening to really cool talks about, edge computing and, cars that are talking to each other in the traffic and the related cybersecurity issues which are apparent. And at that point of time, I started thinking about critical infrastructure, and the question came to my mind. So how do you know if you are being lied to? So how do you know if you are being lied to? Can you imagine the consequences of such a situation with critical infrastructure? We have had two excellent presentations here about, a smart factory, and also about, water plant. What happens if the decisions are made based on wrong information? That is catastrophic, isn't it? So that was the beginning. However, I have to say that I had no idea what kind of journey this could be. This talk is more about building stuff. So I'm an engineer, not a scientist. And the Stuxnet was not actually the primary thing at the beginning. I was just, perplexed with the question of how do you know if you are being lied to. If we put this to a slightly more scientific setup, this research is a practical detection of record and replay attacks without access to the originating infected system or malware. About me, I do my daily work at WebEyes. I do OT security. I'm a leading security architect of the company. And this research has been done in Jyväskylä University of Applied Sciences, JAMK. And I am very grateful that they had the patience with me in this one. So let's talk about basics of cybersecurity. The CIA triad: confidentiality, availability, and then I stands for integrity. And I can tell you that with security people, the I is the least sexiest thing you can imagine. It is the most boring stuff in security. And I'm a hacker, so I play in the red team. And it sort of surprises me as well if that I ended up, working with such a boring topic after all. But if you think that the map here is depicting the Stuxnet malware spread at the time. Who here remembers Stuxnet malware, the worm? Few hands rise. Okay, excellent. The Hack Lab is on board as well. Stuxnet is a worm that was created as a cyber warfare, first of its kind. And interesting thing about it is that even though it was directed to one particular place, which is a nuclear power plant in Iran, this is the spread of it at the time. So when it comes back to, is integrity a boring thing? I don't think so. After this experience. So let's talk about the research target. So we need a data integrity loss detection mechanism that is capable of creating situational awareness. Situational awareness. Anyone who has been dealing with geographic information systems as I have knows what a situational awareness is. It's all about the OODA loops and such things. Also, we needed implementation with predictive neural networks for preventing poisoning of the detection capability. A third thing, we needed implementation of a mechanism to overcome missing common data model. I will talk about this at length in a bit. And lastly, a proposal for Defender, which asset to protect, because there is, if you are doing security and then you have a project, please always remember to mention which assets need to be protected here. This is the way to get the 5 every time. So I must say that the neural networks were not the first choice of mine. I was first thinking about everything else. And let's see all the dead ends that I went through. Database write logs. Old thing. Every single relational database in this world is implementing database logs. Those are used to manage concurrent attempts to write to a database cell. Makes sense. But a database write log does not know a lie when it sees one. So, no answer. What about blockchain? Yeah, well, there's this little thing about the embedded systems. They don't have the computing power. So, and then also from the logical point of view, being able to prove that a piece of data existed at given time does not make any statements about the correctness or integrity of an automation process. And we are talking about automation process here, not network traffic. This is not IT. This is the actual, chemical plant stuff. And Ralph Langner, he's one of the few in this world who has spent extensive amount of time investigating the malware itself. He and his team, and he has given few really gripping, really great talks about it in many places over the years. But also Ralph Langner pointed out that the major vulnerability that Stuxnet exploited was that the present controllers do not allow for digital code signing. That situation has somewhat changed after that, probably because of this. Intrusion detection, intrusion prevention systems. Well, yeah, close but no cigar. You see, a chemical plant is not a network system. It's not an IT network. So these guys don't work there. It doesn't tell anything about the state of the natural process. And also, there's this little annoyance that these IDS, IPS systems can be poisoned rather easily if you want to, over time. So. And then the situational awareness. Footprint of an intrusion does not tell about the state of integrity. So if you know that you have a boogie in your system, it does not tell anything about the integrity of the data. Yes, welcome to the rabbit hole. So let's raise the bar. What if? What if we move the data out of its originating system and combine it with data from other sources? Because this is exactly what we do when we, collect data from, different, sources and start making decisions based on that for the critical infrastructure of society. That is exactly what happens. And what if we only had the data from the cyber-physical process and no access to the originating devices, those little sensors over there? When the data is being used in an ecosystem, you no longer can, call back to those sensors. That's a no-go. So, how to manage integrity of relational data streaming constantly from cyber-physical process. And then the streaming thing here is a significant thing. Please keep that in mind. About the building. So what do we need for a good system? It needs to be test automation compatible, deployable in a pipeline, works with the CPU, vendor independent, cloud compatible and cheap. And data engineering must be done on the fly. There's a reason for the CPU. You see, when I was building the lab to actually build these pipelines, I was limited with choices. I had a MacBook Pro late 2013 with CPU at my disposal, and I did it using that. It can be done. It required a few tricks, but I'll talk about that a little later. Okay, so there is a lot of different data models at play here. And every component and every message of a component has its own. And usually in the embedded systems, there's a thing called HMI, human-machine interface, and also a historian database, which is usually a relational database, like your usual Oracle, if you want, something like that. Very mundane stuff. And it is there because it's collecting and normalizing the data to be watched at one place. And of course, all of us who have been doing IT and ICT transformations know what happens when you have a lot of data and you have to do an IT transformation. It usually turns out to be a hell in one way or another. So I wanted to avoid it, to have the need to actually collect clusters and eons of data. So the solution had to be kind of dataless, if you like. So let's talk about machine learning and neural networks, because when I realized that, okay, the neural networks was the way forward at the time, I encountered a little problem. Well, this is a relational data, and at the time, there were few things that actually were capable of processing relational data in terms of neural networks. So I thought that maybe I encountered a dead end again. But I didn't give up at that point. I also realized that I need a self-learning system resistant to poisoning and capable of predicting future. It needs to be able to form the common data model for relational data with different original data models. And of course, we needed tools to implement the solution. And then, lo and behold, does anybody remember these pictures? These are really famous ones. We have some machine learning people here. No? So this is a commonplace with LLMs on nowadays. But in 2017, it was a major news when somebody was able to create with machine learning algorithm, people who didn't exist. And these guys were using relational data. And I was like, yes, there's a way forward. So let's talk about the boring stuff for a while. So the solution that I found was combining graph convolutional networks and variational auto-encoders. And I'm standing in the shoulder of giants here because both of these implementations actually pre-existed. They were rather recently published, and I realized that, okay, this is a tool that I can use. And the variational auto-encoder is the thing that can predict the future. It's doing link prediction. And link prediction here is vital because that is actually the way of creating the future profile of the data. And this is something that the attacker cannot anticipate. I will show how it works. All in all, this package it's kind of executable, resembling a filter that returns the values of all functions at once in a machine learning execution environment. Myself, I have been thinking about this particular thing like, well, it's like a compression algorithm, except that it produces a cat. You can shoot me now, the data scientist, but this is how I think about it. There are a couple of things that are needed for the calculations. First of all, we need the graph, which is basically, just a network of nodes. And the graph expresses the relations between the nodes. And can you imagine what is the source of this graph? Why this graph was born originally? Because I find it fascinating, because this is from the social sciences. This is really famous one. A study in the 1970s in the United States in a karate club on how people are actually, mingling together and who is friends with who and how these, liaisons, change all the time. But the graph is the same. What is not there is the adjacency matrix. And the adjacency matrix here, depicts, the closeness and how the nodes are sort of, connected to each other. And the graph is processed in memory as a matrix. And now we are stepping closer to the common data model in the memory. Each of these nodes has many features, and many nodes may have the same feature. And hence, a group of features in this world it's called bag of words. And the data sets from different sources are combined by in-memory data engineering into one graph and one bag of words, and then processed further to programmable objects into a common data model. It is incredibly hard to create, any mildly compelling, graphical presentation of this. On the corner, that checkered thing there, that is how the combined data looks if you look really far from it. So that's it. So pretty boring stuff. But then the data in the common data model is fed into training and machine learning model, and later for link prediction. And then, of course, since we want to be sure that we are getting some meaningful results out of this, when you combine two data sets, you actually have to test that the combined data set is performing with the same accuracy level as the separate data sets would perform. And in this case, the accuracy of Thomas Gibbs' implementation was 80%. And here is how it basically classifies the combined data set. This video is here because I speak in hacker conferences, and we have a rule that POC or die. In this case, it's POC or die of boredom, because this is as fun as watching a washing machine to wash. But as you can see, the test runs nice and smoothly, and we are getting where we want to. Then let's talk about the common data model. This is Python from now on. And it's really difficult to explain what a data model in this case actually looks when it's in memory, because it's like, well, a cube with additional humps, a tuple, a dictionary, a list clinging to each other. And I can tell you, when there's an error in this, it's really mind-boggling to try to figure out, which of these is not in the place. Okay, and then I wasn't happy, because I'm a hacker, and we need to test this the hacker way. So one of the problems back in the days, I hope the situation has become a bit better. But back in the days, the problem was that very often the results of machine learning research were affected by the fact that they were using the same data for both, creating stuff and then testing the stuff. And it has a knack of actually, distorting the results in a way that we don't want to. So I needed something that can produce for sure 150% not same data as what I had been using for training my models for the detection, but that would be similar and then also relational. And then I found reinforcement learning. More machine learning, yay! And there was at the time also research on how reinforcement learning can actually, create a false and adversarial, results created by other machine learning algorithms. So this is kind of a liar as well. A liar in the story, by the way, is Stuxnet, because what Stuxnet did was that it actually, recorded the telemetry for about 6 months, and then when the attack was activated, they just replayed the telemetry. And for that reason, it took the longest time in the Natanz nuclear power plant for the engineers to realize that what was going on, because the telemetry in the HMI was nominal, and then the centrifuges in front of them, 2 meters away, were exploding. So this is the liar. But I had a chance to actually make 2 proper attacks, a data degradation attack and a record and replay attack. In the data degradation attack, I did a partial replacement of good graph with adversarial data. And then the record and replay attack, I did a full replacement of graph by repeating adversarial graph until the length of the good graph was reached. And this is how you do it. So on your left, you have these 2 gray boxes. Each of them has data in there. And the other one is the malicious, the mangled data, the data that we have just received from the live system. The relational data that has streamed from the factory to our table. And then on the lower corner, we have the data that we have already, took in, and we know that this is good. And now we need to figure out, okay, so can I, omit this new data to my existing data, or is it going to be poisoned? So how do I know if I'm being lied to? The predictive model for these 2 different, data bunches, if you like, is the same. And then we run the predictive model on both data sets. And lo and behold, the result is not the same. So there is a distinct difference between the end result of these 2 trainings. And of course, if there is a deviation, there should be alarm, following the practicalities of any good security system. And here are the guys again, the graph and the adjacency matrix. What I did was that I simply compared the adjacency matrices. I put them on top of each other and look at how much they differed from each other. And it was possible to see difference in the link prediction by comparing these adjacency matrices. And only about half of the predicted maliciously modified relations matched with relations of predicted protected dataset relations. Some learnings. Link predictions seem to be a feasible thing to do to compare datasets with no common data model. So check, we have a common data model, even though the data comes from different origins, different systems altogether. Then graph convolutional networks and auto-encoders bring the ability to predict the future data profile. I have to say at this point that for this thing to work, you need to have a finite problem. So what this thing does, as far as I understand, is that it's like you have a huge puzzle in front of you, and then you have a few extra pieces that have not found their place yet. And then this thing tells you that these three things are the ones that you are missing. So this thing can tell you that, okay, you need to put the blue dot over there. It should be there. So that is the kind of prediction it does. Differences in predictions can be detected and the poisoning can be prevented. I thought about the poisoning in a sense that when you make two predictions and compare them, it also means that when the attacker only sort of has access to the incoming data, to the new data, then the attacker has limited means to actually know what kind of prediction is going to be born out of the protected dataset. So it's kind of in a different channel, as security people tend to say. They can't mingle with the result. In order to maintain this capability for a defender, it is important to be able to control the building blocks, which is the graph data and the back of words. So those need to be protected. The original relations and features of data remain unchanged, which is important because otherwise we would again be meeting with a huge data transformation issue, and we wanted to avoid that, didn't we? And of course, there is no need to create a new relational or non-relational database to manage data from different sources. So that should be also something that makes the IT department very happy. This is a grab and carry model. The solution is storage efficient due to small size of machine learning models. And the machine learning model can be refreshed as needed, and it should be over time. And this is programmable. It can be put to a pipeline, and it is cloud compatible, although I did not do a cloud implementation for this. So before I go to the, I seem to have some time still left. Before I go to the technical implementation in detail, I wanted to give a shout out to Thomas Kiff and then Dai and Song for their outstanding work, which helped me make through this. And of course, Ralph Langner who has been done great work in dissecting a cyber warfare weapon called Stuxnet. Before I go to the technical implementation in detail, are there any questions at this point, or comments, or please? Well, I would run this in a place where you collect data to a data ecosystem, which means that you have 5 factories. One of them is a metal factory. One of them is a nuclear power plant. One of them is a chemical, plant. One of them is a water facility. So this is agnostic. This is interested in data, not place. No. I mean, I'm not made of money. You see, I was a poor student at the time. So please forgive me not implementing a huge, national scale stuff. But it works there. It has been done, that in mind. The final calculation with the meager means that I had in my hands took 40 minutes, which is still reasonable. But it is safe to say that if you have more data, then of course you need more computing power to run this. That goes without saying. And there the laws of physics are like the limitation, I guess. But that was a good question. Okay, shoot me. So I encourage you, sir, to look into this, excellent paper. Learning combinatorial optimization algorithms over graphs sounds very, awesome. But what this research team basically did was that they found a way to use reinforcement learning algorithms to actually produce false models that would be otherwise naturally provided by convolutional networks. So it is that kind of a lie what they were researching. And I was interested in just about the data, because if I had a mangled graph convolutional network like model, I can produce that data as well. So I was kind of piggybacking on this one. And this very much stands on its own as research. Really, really good paper. Warmly recommend reading this. But yes, it was not, let's say, it didn't come to my mind that I would end up in this rabbit hole with this question eventually. I thought that the answer might actually be found from somewhere else. But here we are. Okay, so technical implementation. It's Jupyter notebooks and Docker containers. The reinforcement learning implementation was actually originally coded for CPU. I don't have a GPU in my Macs, so I had to port it. Luckily, it worked after that, as it should. So that was a bit of a hairy moment, but anyway, Also, I would like to mention that with all this, 95% of all the work is data engineering. It's just gruesome amount of data engineering, and the rest like 5% is like flying high. But there you go. I wrote a lot of Python code for combining those datasets. And then, of course, when you think about a lab like this, I tried to think about the sort of the isolation from the beginning, and that is why I created these, Docker containers. Each one of them run an independent Jupyter Notebook instance in it, so that I was reasonably sure that the results were not, mixing up. The processes were not mixing up with each other. And on this side, I had the so-called the test container, which was used to actually, test if the combined datasets were reaching the 80% accuracy that Thomas Kipp's graph convolutional network implementation was promising. So that was a quality test for the data. I needed to be sure that my data engineering had, well, gone to the right direction and not south as you would. It's really easy to make mistakes there. Also, I needed to isolate, of course, the reinforcement learning to its own little world, so that I could be reasonably sure that the data that I was getting out of it was more or less, reliable in that sense that I can safely say that it is not the same data as what I used with the predictions. And then the final container is the one that actually, does the comparison. Takes these two datasets in, calculates the classification and link prediction to both datasets, and then, finally, it compares the adjacency matrices. And there I had the results. So, yes. That's it, folks. I was a bit faster than I thought.